Alrighty, I have no idea what to call this video. Just something I've seen in the last just hour, 2 hours. And it's really about putting polynomials in graphing form and the importance of minus b over 2a minus b over a minus b over 2a minus b over 3a minus b over 4a. I know in the 90s I went to a 7th degree polynomial with the help of a computer to get rid of for the 7th degree, you get rid of the 6th degree term for a graphing form. Well, in the quadratic, you get rid of the linear term. In the cubic, you get rid of the quadratic term, so on and so forth. And you can, simplify, you get fewer terms in the polynomial expressed graphically in graphical form. All right, you can tell my language is a little off. All right, but what got me thinking about it was the take out what's common video. All right, and then I was thinking, well, units of measure. So if X was meters, then we got meters to the fourth here. Well, then we got to get the same thing on the right side, meters to the fourth. And we get the drawing, we take out what's common, we take out what's common, we take out what's common, take out what's common. And we can see that we've got to get, some kind of squared term, but there's a constraint here. So I don't want to get into this too much more, but that's what gave us plus minus 3 as answers. And I'm not going to belabor the point. There's the factored form. You can see plus or minus root 3. All right, so I've been thinking geometrically here. All right, so let's start with the linear function. And let's just say that 1 unit times ax plus b gives us some amount. Didn't mean to make it into a, I'm not even showing you this. Renee, you should have a voice box and let me know. So start again. So 1 times ax plus b, if that's 0, we get a root, and that root is minus b over a, and the significance of it is you get a sign change. The line was coming the other way, we'd go from positive to negative. This one's negative to positive. All depends upon what a is, positive or negative term, right? And so, for instance, if you had 3x plus 4, then minus 4/3 is the average of the roots. I've been saying that for a long time. And minus 4/3, I think, is more important than the y-intercept of 4. Because more things happen there that are leading into other things that we do when we try to find whether a polynomial is positive or negative, so on and so forth. So I think we should really be thinking about minus b over a rather than plugging 0 in and saying the y-intercept is b. Now, where does that go when we get to the quadratic? Well, we talk about completing the square. Well, what's completing the square? It's really taking the first 2 terms, which is really a rectangle. I mean, I got one over here, but the length of the line ax plus b, I really could probably not have done that. I don't know. As I say, I'm just starting to think about this. But we can see that C is not really a part of this completing the square process. I have to make the longer side shorter, the shorter side longer. I'm sure in the quadratic section, there must be a completing the square video where I take the time with some easy numbers to look at and to try to understand that process. But it's really about evening off the sides of this rectangle. And if I did put x equals 0, then 0 goes through C. I hope you can see 0 times anything is 0, I get C. And if I put minus b over a in here, I get no area in this rectangle, and I get C. And so what's in between this distance, because I'm creating a 0 here, that distance is minus b over a, and half of that distance puts me at the vertex. So x equals minus b over 2a. Lets us find the x value of the vertex of a quadratic quickly and easily. Then, of course, you plug it back in, find the y value, and you're off and running. All right, so let's look at the cubic. Now, what I did is I played with the first 2 terms in the quadratic. I should be playing with the first 2 terms here to explain this better. All right, and if I did, what's common is x squared. So x squared times ax plus b. Notice that's showing up in all 3 situations here. And I just did 1 to the 4th power, and it's going to show up over there too. But for right now, ax plus b is the distance from 0. But in the cubic, we're not cutting that distance in half like we did with a quadratic, right? And I think I did this, maybe I didn't do it with a number. All right, so, okay, back to where I was. We can see this x squared times ax plus b is either going to look like this or this. That's a double root. All right. So if you put this in a grapher, and let's just talk about x squared. Let's, I got one here. All right. So I've got one here. So if I'm looking at x squared times 2x plus 15 minus 15 halves is where this cuts through the x-axis. This is my double root, and that is what I get for a graph. Now, that distance is minus 15 halves. Minus 15 over 6. How does that compare to minus 15 over 2? Well, that's a third of that. And a third of that would seem to be about here. And what does it link up with? It links up with the point of inflection of the cubic. Now, I do remember 20, 30 years ago, looking at the graphing form for the quartic, and I couldn't figure out why it was off-center different places. Now I understand, because minus b over 4a, minus b, so x cubed times, here's your ax plus b again, showing up again. So 2x minus 5 is minus 5 halves, so let's call that minus 5 halves. If I take a fourth of that distance, and I'm not graphing, I will get a spot on the graph, which, if I take this and complete the quartic, can't draw it, right? But it's based on the 1/4 distance from this. All right, this is awkward, all right? But I'm just going to put it out there anyway, because it's a truism. And if you play with the graphs, you'll see that if you wanted to look at very quickly, again, let's throw 5x cubed minus 7x squared, very non-friendly numbers, right? Plus 2, if I take out what's common from the first two terms, I've got x squared times 5x minus 7. Okay, I got 7/5. That's the distance from 0. If I divide it by 3, the division by 3, I believe, is evening off the 3 sides of the cube that can be created. All right, so if I even off the 3 sides of this cube, I only have whatever this length is, whatever makes that 0. That's all I have for putty. It's the only putty I have. And therefore, if I'm going to make a perfect cube versus something that's not a perfect cube like this, those sides are not all equal, and I'm not drawing it well. Yeah, not too bad. I drew it, not too bad. The sides aren't equal. If I'm going to equal them off, all 3 sides have to be the same. And if I can take out what's common, and it's always a 0, then all of the putty comes from the distance to that actually change of signs from negative to positive, positive to negative, because it's linear. Okay, so it's just something to think about. And I'm going to be thinking about it. Because it can then be used to explain the graphing form for the 4th degree, 5th degree, 6th degree. I don't see any purpose for those. Then again, who knows? Maybe there is one. All right, so that's a little awkward. Sorry. But my first attempt at explaining something. But the way I teach is we don't stop looking at it. So I'm hoping I can explain it a whole lot better 3 months from now. All right, but there's something going on there. All right. I don't know. All right, we'll see you.